Hello everyone. Today I will be discussing the concept called as the standing wave and standing wave ratio. Dear student friends, in the previous classes we have already studied the microwave transmission line equations and also the solution for those transmission line equations. And here you have come across with the two types of waves. One is incident wave and another one is a reflected wave. And both those waves are having unequal amplitude and opposite direction. And one more point I want to bring to your notice that whenever there is a transmission line which has got a source as well as load, and the characteristic impedance of that transmission line is denoted by Z0 and the load impedance is denoted by ZL, and whenever the load impedance ZL is not equal to characteristic impedance Z0, then we call the transmission line as the short circuited transmission line. And under that condition there is a waves which propagates in the reverse direction, that is exactly opposition direction to the incident waves, and those waves are known as the reflection waves. And the combination of the incident wave and the reflected wave tends to a new type of wave known as the standing waves. So here we understand what are the standing waves. These standing waves are nothing but waves combination of the incident wave and reflected waves. Both they are having unequal amplitude and they travel in opposite direction, and mathematically they are given by V of Z is equal to V plus e raised to gamma Z plus V minus e raised to minus gamma Z. So it is e raised to minus gamma Z. Both V plus and V minus, they are the amplitude or magnitude of the incident wave as well as the reflected wave respectively. And this gamma is a propagation constant, and both the waves travel along Z direction, right? So in simple form, the standing wave representation is given by V of Z is equal to V naught e raised to j theta, and this V naught is the resultant magnitude of V of Z, and this can be expressed in terms of V plus and V minus. And similarly, this theta is known as the phase which corresponds to the direction of the standing wave, and this theta is given by this mathematical equation tan inverse of this divided by this. And this equation number 1.97, which is given by V of Z V naught e raised to j theta, is referred as the voltage standing wave representation, right? And this 1.98 equation is known as the standing wave factor, that is the magnitude pattern you can call, and the equation given by 1.99 is known as the phase pattern of the standing wave ratio, right? So as I said, when the transmission line is not terminated, when it is open, in this the characteristic impedance Z0, right, then there will be no reflection of waves, right? So whenever the ZL is not, ZL is equal to Z0, then there is no termination in the transmission line, and hence there will be no reflection waves, right? So the transmission line is not terminated. When it is not going to terminate? When ZL is equal to Z0. Right? So that you have to understand here. Sorry, I will correct my statement here. Whenever the ZL is not equal to Z0, ZL is not equal to Z0, there is transmission line is not terminated in its characteristic impedance. Therefore, there will be a reflection of waves. The reflection of waves occurs only when there is mismatch in the transmission line, that is ZL is not equal to Z0, and the combination of incident and reflected waves gives rise to the new form of the peaks known as nodes as well as antinodes, resulting in the standing waves. Means these standing waves consist of nodes as well as antinodes. And these nodes having the maximum amplitude and antinodes are having the minimum amplitude. So in this figure you can clearly understand, you will get the feel of how the standing waves looks like. So this is how the standing waves looks like, right? So here we have antinodes as well as nodes. So this maximum amplitude peaks are nothing but antinodes, and this minimum voltage points are known as nodes, right? Then when line is terminated in an open circuit, right, then a ZL is equal to infinity, a considerable voltage exists across open circuit. Thus an antinode is formed at the open circuited end, and both antinode and node you can place according to the voltage as well as current, right? So the node is created at a distance of lambda by 4 from the open circuited end, right? So I will explain here. So this is the open circuited end of the transmission line, right? So this is the receiving end, that is the load side, and here we have antinodes, right? So this continuous line corresponds to what? If this continuous line is corresponds to the voltage, and this dotted line corresponds to what? The current, right? And the antinodes correspond to voltage are located or placed at a distance of lambda by 4, right? Lambda by 4, 3 lambda by 4, 5 lambda by 4, and 7 lambda by 4. Similarly, for current, they are located at what? 0, lambda by 2, 2 times lambda by 2, that is lambda, and 3 lambda by 2, so on, right? Similarly here, you can observe one more, that is the short circuited end of the line, right? So whenever there is a short circuited end of the line, right, the antinodes, so here given, these are the nodes occur voltage, right? And it is also seen that current nodes are occur at distance 0, lambda by 2, 3 lambda by 2, and so on. Nodes, so you can observe here, right? So these are the nodes, lambda by 4, 3 lambda by 4, 5 lambda by 7 by 1. This is corresponds to what? The voltage. And for current it is 0, lambda by 2, 2 lambda by 2, and 3 lambda by 2. Similarly, for short circuited end, right, you can see it. Again these peaks are antinodes and these are nodes, right? So now let us note down where the node points are located for both voltage as well as current. So this continuous line is for voltage, and this dot lines are for current. So first let us see for voltage, and for voltage the nodes are placed at located at distance 0, lambda by 2, 2 lambda by 2, that is lambda, then there is 3 lambda by 4, then 2 lambda by 4, right? So similarly for current here it is lambda by 4, 3 lambda by 4, 5 lambda by 4 and 7 lambda by 4, right? And when the dissipation less line is terminated in its load impedance ZL, then no standing waves will be observed and there will be no variation of voltage as well as current along the transmission line. Unlike how we have variation in the voltage and current along the transmission line, because here it is there is a combination of a reflection as well as incident waves, right? So when there is dissipation less transmission line, that is ZL is equal to R0, then there is no combination of standing waves at all. So when there is no combination of standing waves, there is no matter of the standing waves. When there is no combination of incident and reflection waves, there is no matter of standing waves. Therefore there will be no variation in the voltage as well as current along the transmission line, and such terminated transmission line is known as what? A smooth line, because there is no change in the amplitude of voltage as well as current, right? And for short circuited termination, as I explained through the diagram, the voltage and current standing waves appears as the voltage nodes occur at 0 lambda by 2 lambda 3 lambda by 2, and the current nodes occur at lambda by 4, 3 lambda by 4 and 5 lambda by 4, right? So this is the brief idea given regarding the standing waves. So what are standing waves? Basically it is a combination of the incident wave as well as the reflected waves, right? What are antinode and nodes? So the antinodes are corresponds to the voltage having maximum amplitude and the nodes having minimum amplitude, and both nodes and antinodes resulting standing waves. And then here you can see the standing wave factor with respect to the amplitude as well as direction along z-axis. Then so whenever there is a open circuit, that is ZL is equal to infinite, so across open circuit, right? So one thing you have to remember here is when ZL is equal to Z0 is known as what? The open circuited. When ZL is not equal to Z0, it is known as what? Short circuited. And during ZL is not equal to Z0, so there is a reflection waves occurs, so hence the standing waves results. And then we discussed how the nodes are occur with respect to the open circuited end of the line as well as short circuited end of the line. And when there is ZL is equal to R0, the standing waves are not there, therefore there is no variation in the voltage and current along the line, and such transmission line is known as smooth line, right? And let us go with one more important terminology in the transmission line, that is known as standing wave ratio, right? So it is a very simple concept, and here the definition for the standing wave ratio is given by, it is a ratio of the maximum to minimum amplitude of voltage or current over a line having standing waves, right? So whenever there is a standing wave which propagate along a z direction, and we know that in standing wave there is a variation in the voltage as well as current, right? At some point the voltage will be maximum, at some other point the voltage or current both having the minimum amplitude, right? So whenever we have the maximum amplitude and minimum voltage for both voltage and current, if you take the ratio of maximum amplitude to the minimum amplitude, that ratio is known as the standing wave ratio, and symbolically which is denoted by rho, which is given by V max by V minimum. And in terms of current, the same standing wave ratio is defined by maximum current to the lowest current, that is minimum current, right? So in the previous classes you already studied about the parameters like the transmission coefficient and the reflection coefficient, right? So to define or to calculate the standing wave ratio rho, most of the time we use the transmission coefficient, that is tau, right? So let us relate the transmission coefficient, reflection coefficient with the standing wave ratio, right? This relation is given by, I am not going to discuss this derivation part. You just remember the relation between the reflection coefficient and the standing wave ratio. The relation is given by what? The rho is equal to 1 plus the magnitude of reflection coefficient divided by 1 minus its magnitude of reflection coefficient. So this is the very important relation we have to remember. This will be helpful in solving the numerical examples, mainly on the standing wave ratio, right? So this is a relation where the standing wave ratio is defined in terms of the reflection coefficients. So now let us rewrite this equation for the reflection coefficient in terms of the standing wave ratio, right? So that is given by this equation. The magnitude of reflection coefficient tau is equal to rho minus 1 divided by rho plus 1, where rho is the standing wave ratio, right? And one more equations we have is in terms of the maximum and minimum voltage of the standing waves for the reflection coefficient tau, which is given by Vmax minus V minimum and divided by Vmax plus V minimum, all are in magnitude form, right? So if it is possible to measure Vmax and V minimum for standing waves, then using this equation you can calculate what the reflection coefficient, and using this reflection coefficient you can calculate the standing wave ratio, right? So these 4 equations are very important. I will go through these equations, right? The first equation is what? Rho is equal to this one, 1 plus tau, this one. Where is that equation? Okay, that is a very beginning equation, that is the definition of standing wave ratio. Yes, that is Vmax by V minimum. This is the first equation for rho, and the second equation for standing wave ratio in terms of reflection coefficient is this one, and the reflection coefficient in terms of standing wave ratio is this one, third equation, and finally the reflection coefficient in terms of Vmax and V minimum. So if you remember these 4 equations, you can solve any kind of numerical if they asked on the standing wave ratio, right? So let us take one simple example, right? The problem statement goes like this: find the reflection coefficient and voltage standing wave ratio of the line having R0 is equal to 100 ohm, ZL is equal to 100 minus J 100 ohm, right? So ZL and Z0 is given. Use the formula reflection coefficient ZL minus Z0 divided by ZL plus Z0. So write ZL, right, and minus Z0, ZL plus Z0, 100 minus 100 get cancelled, so you will get minus J100, and after simplifying denominator you will get 200 minus J100 ohm. So they are in rectangular form. For the simplification purpose, you convert this rectangular form into polar form. So you will get magnitude 100 with a phase minus 90 degree, and for this one you will get 2 to 3.61 magnitude with a phase of minus 26.27 57 degree. You divide this magnitude, you will get 0.4472, and subtract these magnitudes because they are in division form. Minus 90 degree minus of this minus 26.57, you will get minus 63.43. So this is the reflection coefficient, and use the relation rho is equal to 1 plus tau, 1 minus tau. Since it is a magnitude, you have to consider only this part, 0.4472. So substitute, so you will get rho is equal to 2.618. So in the next class we will discuss one more example.